Then I want you to also figure out, why did I draw this dotted line in here? What happens at that dotted line? Okay? What happens at that dotted line? So I want you to look at the y and x-axis, concentration and time, your given reaction, and the chart. So go ahead, take a minute or so. Which one is A, which one is B, which one is C, and what happens at the dotted line? So, think about it. Come up with answers in your head. Then you put that one first. Just make sure you put it away. Anyone else? Catherine, Caitlin, get your phones out. Put it away, please. That's right. You just put it somewhere so I can't see it. Nice. Okay, that was about a minute. Turn and talk to somebody about what you think. Go ahead. Turn and talk to somebody about what you think. Let's go. So get Althea involved here. Zane, share with Althea. Saffron, if I was your partner, what would you tell me? You got to tell me something.
All right. Yeah, that's what.
What do you think? Your partner's in you're going to help Kat. She said she doesn't know. You have an idea?
A would be 2 NO2. Next time. I mean, just go to O2. Yeah. C probably 2 O2. So it's just no C. The other way around reactants.
Okay, talk to somebody. All right, Abby, share with Zach over there. Kai, what about you? What are you doing?
Huh? I'm doing it right now. I'm writing it in the book.
All right. Yes.
I think it makes sense.
John Todd. What do you think? You and Justin think you come to an agreement here? What do you got? A is N2. B is 2O2. C is 2NO2. You got one of them right. C is the NO2. C is definitely the NO2. Pay attention, please. C is definitely the NO2. But we're going to flip what they say. O2 is A, N2 is B. Now, let's think about what's happening. Now, I probably should have given you a little more information. I should have said something to the effect, inside a sealed container, some N2 and O2 are pumped in. After a while, a reaction occurs and NO2 is formed. So usually what happens with equilibrium reactions is you start with just reactants. So you start with these two. Just these two. And then as they react, you're going to see the products start to form. So think of it just like this, the balance beam here. All reactants. We don't have any products yet. They haven't reacted. They haven't collided, right? They haven't collided. So once they collide effectively, they will shift and they will form some products so it will be balanced. So usually there's a little more information. I was just throwing it out there to see what you guys thought. So the reason C is NO2 is because it starts with hardly any concentration. So in general, all reactions, you start with reactants with high concentration and products with very low concentration. As they collide, as they react, it starts to shift towards the product side. That's what's happening here. As N2 and O2 actually collide and react, they start to disappear and they turn into, chemically, turn into NO2. So as these two react, their concentration decreases. That's like taking some of the weights and just shifting it over here. Okay? So as some of this reacts, it's going to decrease in concentration. What happens to products? It increases in concentration. So your products start out with very little and then increase in concentration as it reacts. Your reactants start out with a lot more and decrease as they react. Okay? Long time ago, I started this whole equilibrium thing. I think I did, or reactions with making peanut butter and jelly. So let's say this is your peanut butter and your jelly. Before you open the containers, they're full. As you make sandwiches, the jelly and peanut butter is going to decrease. The level is going to decrease because you're using it. Well, look at this as the sandwich. You start out, you don't have any. As you make the sandwiches, you start to make more and more and more, so the sandwiches start to accumulate. So your peanut butter and jelly decrease, your sandwiches increase. Just an example for you. So these two are definitely the reactants because they're decreasing as this reacts, as time progresses. This is definitely the product because it increases as time progresses. It has nothing to do with where they are as far as, well, this is confusing because why is the product below the reactants? That has nothing to do with it. What it has to do with is the beginning. Is which ones decrease, which one increase. Okay? The reactants will decrease initially, products will increase initially. Questions? That's really important what I just went through. Sydney, did you listen and pay attention?
I spelled some stuff.
Okay. So, why is A O2? So C is definitely the product, but why is O2 A and N2 B? How come it can't be flipped? How come I can't say A is N2 and B is O2? Jack?
There's more moles of O2 than there's O2.
Right. This is higher because there's more. It's a 2-to-1 ratio. So there's more O2 to start. There's more O2. Hopefully that makes sense to you guys as well. Now, Abby, what happens after the dotted line? Anything that you want to say is good with me. Anything. It could be literal. It could be where they're all equal. What does that mean? They all have the same concentration. See this word right here? Of course you do. This y-axis means concentrations increasing. So, let's rephrase what you just said. Let's say we had numbers here. 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 100. Would this concentration here be the same as this one? No, and it wouldn't be the same as that either. So, that's a little bit high, but, so I like what you're thinking, you just said it wrong, and that's okay. That's why we're doing this, to help us learn how to say it or write it. So the concentrations aren't equal. Some of you hopefully are seeing where I'm going with this. Don't say it, Abby's going to get it. The concentrations aren't equal, but they aren't changing. So what's that word? Starts with a C. It's okay if you don't. Constant. Shh.
I didn't say it.
Oh, somebody did. But yeah, it's constant. It's constant. So, I didn't mean to put you on the spot, Abby. Good job. So, constant. So, this is really important because there's a bunch of questions on your quiz, not with this picture, but very similar concept, that this is a very good example of what I mean by not equal, but constant. So, because this is at equilibrium, the rates are equal, right? We're forming products and reactants at the exact same time. Their concentrations are unchanging. So this point right here, that's where equilibrium is established. So right here we're not equal, or we're not at equilibrium. So when it balances, that's where that line is dotted, right? That's where that line is
You
dotted.
might be out of space.
Oh yeah,
right
you
now.
trying to record? It's not.
You might be out of space.
No, it's working. It just says someone's using it for FaceTime. But thanks for the heads up.
I have a
It
question.
looks very similar, the same
Yeah, I
message.
could read it.
Yeah.
Why does it matter where the O2 is? Like, why could the N2 be it?
Why does it matter? Good question. So again, Sydney, you with me?
Yeah.
Okay. Why does it matter where the O2 and N2 is? Because of the mole ratio. You have twice as many moles of O2, so 2 is bigger than 1. So if this is concentration, O2 is going to be higher than N2. That's the only thing.
Okay.
Okay. Again, after this point, equilibrium is established, so the concentrations don't change. They stay constant. Okay? So I go through this because it's confusing. It is confusing. We didn't do anything in our notes like this, but that's okay. Just seeing a practice problem. I have another worksheet I'm going to give you maybe Wednesday. That's tomorrow or Thursday, to practice a little more questions like this. All right, we do need to move on and start getting into organic, but I want to put up one more practice problem here, so you guys can leave that alone. Just hit the lights, please, real quick. Actually, you know what? Forget it. Forget it. We don't need it to be dark. Just a sample problem. So I'm going to put this up here, and we will go through this. Now, tomorrow, I think what we'll do is a couple practice problems with the reaction rate stuff. Because we've been kind of pounding this equilibrium pretty good here. All right. Hold on a second. See if I can do this. There we go. All right, so there it is. It says, given the equation representing a system at equilibrium, that same reaction we use all the time, which changes occur when the temperature of the system is decreased? Can you guys all read that? You guys ready? Good? No, you can't read that?
It's just because there's a glare here.
Oh, it's not because it's too small?
Just pull things up.
Hold on. Give me a second here. Oh, maybe that helps. Maybe not. Alright, sorry. Technical difficulties here. Alright, well, so you have a glare sitting almost directly straight on the board. You have a glare? Is it always hard to see?
No.
Just right now it's hard to see. Hit the lights, maybe that helps. Does that help?
No. Well, it's because
It's
You don't have
just
the
board.
board.
It's just the board.
it's just
Oh, it's because of the board, not the thing? Oh, that's annoying. Alright.
See the glare is not.
Alright, so which change occurs when temperature of the system is decreased? So if you guys look at this, first of all, energy's on the right. Exo or endo? Exothermic. So don't say it out loud. Think, if temperature is decreased, what did we talk about yesterday? Temperature is decreased. Can I open a window?
What?
It's warm in here. Can I open a window? Temperature is decreased. Which way?
Is it ready?
Yeah, I don't know. What did we say yesterday, Zach?
The endothermic reaction is favorable.
All right, good. Give me another thing. Give me another way to say that, because some students have trouble with that. I think.
The reversion, the products include.
Yeah, all right. But what did I say yesterday? Talked about being near a fire or farther away from a fire. That, I think, helps some students understand the analogy. If you decrease the fire, if you decrease temperature, you're going to be cold, right? So you're going to shift towards the heat. So which way are we shifting? If we're decreasing temperature, we're going to get cold. So which way do we shift? Right. To the right. So we're shifting to the right. If we decrease temperature, what he said is correct. It favors the exothermic. Exothermic is that direction. So if you decrease temperature, you go towards the heat. Towards the heat. Another way to think of it, energy is just kind of like heat. And if you decrease temperature, that's kind of like removing some of this heat. So you're going to be like this. So you have to shift that way to go back to being equilibrium. So we're shifting right. So if we're going to the right, which answer makes sense? Does the concentration of H2 increase and the concentration of N2 increase? No. If we're shifting that way, these two are going to decrease in concentration. That one's going to increase if we're shifting that direction. So, Justin, what's the answer? 4. Concentration of H2 decreases, that decreases, and NH3 increases. You will see questions just like this on your quiz Friday. All right? There's another one I was going to do, but we've got to move on. So, that's that. And I think I told you yesterday, lights please, Zach, I was going to be after school every day this week. I can't say today. Something came up, so I got to leave basically right at 3 o'clock, a little before 3 today. So, if you want to review for this quiz, I do have a couple review sheets I'm going to give you, and we're going to do this at the beginning of class every day this week, but I'll be after school Thursday. I got a meeting Wednesday, but I'll be after school Thursday. Damn it, I got AP review. I can't stay and review for this quiz. So if you want to review for the quiz, it's going to have to be during a free time, free period. Hopefully these review sheets will be good enough, and whatever I talk about in class. So that's the best I can do. Their AP test is in 2 weeks, so once that test is over, I don't really have to worry about them anymore, so it's a lot easier to have review with you guys. So I apologize for that. All right, take out your notes, please. Let's talk about organic. let's talk about organic chemistry. Yesterday we kind of talked, we're thinking out loud about things. Hold on, I gotta write a note to myself before I forget something. Alright, so, Liam, when I say organic, you think? Carbon. Good job. I need everyone to think just like Liam. Is that cool? You guys think like Liam? You wish? You wish you thought like Liam. Well, I guess that's nice. That's nice of you to say. But I think the way that you think is probably fine. Because you think like Caitlin, and you should be Caitlin. Bless you. However, I know what you're saying. So, organic, think carbon. So, in our notes, did we write organic chemistry yet? No, let's write it. Organic chemistry. Organic chemistry. Alright, here we go. And put a little star here. Put 3 stars. This is triple importance. Only substances containing carbon are considered organic. And that's it. That's all you need to know. At least for now. There's a lot of stuff we're going to talk about. This structure right here has carbon in it. The black ball in the middle, that's carbon. The yellow ones are hydrogen. So in lab, you're actually going to be looking at these. I'm going to have probably period 7 help me because there's more of you. I'm going to have you guys, if not today, Thursday, put together a whole bunch of these structures for our next lab. Just saves me some time. We have to make like, I don't know, 14 structures, and they're all bigger than this. So we got to put together a lot of these wooden spheres. So anyways, that's the most important thing to remember right now. Is carbon. Next important thing, reference tables. Take those out, please. We're going to learn 3 new reference tables. Tell him what he's won, Bob. A new carbon.
Can I throw away some of this stuff?
A carbon car. Whoa. What?
I'll throw away some of this stuff.
Not right now.
What's carbon fiber?
Ah, carbon fiber. It's a very thin material made of carbon. That's all it is. You guys ever hear of nanotubes or graphene? Anybody? No? That's all structures made out of carbon atoms, but 1 atom thick layer of carbon. Who did I show someone in here with the, or explain with the piece of tape and the pencil and the, no? That wasn't you guys? If you take some Scotch tape, or whatever brand it is, but this clear tape, and you, well, first take a piece of paper, doesn't matter, you can take a Post-it note, and shade it with a pencil, so you just have a bunch of shaded graphite on here. You take the tape, put it on that shaded area, and peel the tape off. Then, you have the tape with the graphite on it, and then you fold the tape on itself, on top of the graphite. Then you peel the tape apart again. On either side, you will have one atom thick layer of carbon, and that's called graphene. And that's a big deal in technology and science world these days. The scientists and experts, think that they're going to start making electronics, cell phones out of graphene because it's very strong and very light. So anyways, you want to make some graphene at home, that's how you do it. So Caitlin, if you're bored this weekend, just make some graphene. Alright. So anyways, reference tables, do we all have them out? We all need to have our own. If you need to borrow some, they're over here. Okay, table P. Everyone go to table P. And underneath table P is table Q. What comes after Q? R. Flip and look at R. R is a little intimidating.
R takes up a whole page.
R takes up a whole page, right. Don't let R scare you. Go back to P and Q. We're not going to deal with R for a little while. But P and Q we're going to talk about today. So table P says organic prefixes, correct? Okay. And then Q says homologous series of hydrocarbons?
Yeah.
Okay. So we're not actually going to use it right this minute. I just wanted you to get it out because we're going to be using it today. Just make you aware that those three reference tables are important to remember to use here. So we're going to write reference tables P, Q, and R. They're very, very valuable to you, okay? Do not forget they are there. So, first thing, what did we talk about? Carbon. Anything with carbon is organic. Second thing I want to make sure you understand is where to look in your reference tables to help you out with this organic stuff. And the other thing we talked about is we're going to be messing around with structures like that to help us understand what organic compounds look like. So, some other kind of general things that we need to know before we get into details. Next thing, organic compounds pretty much only contain nonmetals. So carbon with hydrogen, for example, or carbon with hydrogen and oxygen, like sugar, CH and O. Those are very common. So are organics ionic or covalent? If it only contains nonmetals. Covalent. What's ionic? Metal, nonmetal. Isn't that the review book that's due or was due? Didn't you guys just do the bonding chapter? Or is that the one due this Friday?
No,
You just did, right?
This Friday is moles of stoichiometry.
Oh, okay. Last week was bonding,
Yes.
I believe? Yeah. So, hopefully that resonates a little bit. So, organic chemistry, organic molecules are covalent. And I'm going to say usually non-polar covalent. I say usually because there are a bunch that you need to know that aren't, and I'll tell you what those are. But in general, we basically think of them as non-polar. So organic molecules are covalent, usually non-polar. What does that mean? This is a refresher here, bonding. Non-polar. Are they strong or weak substances? Don't answer that yet. Are they strong or weak substances? You remember the tin can lid, aluminum can lid. We put it on the ring stand, put the candle underneath. 3 things melted. Wax was one of them. Does someone remember that, hopefully? The wax melted very quickly, didn't it? Maybe it was like number 2.
No, I think wax was 6, wasn't it?
No, I mean 3 melted and it was the second one that melted, I think. I think wax melted second fastest. I think the first one was that phenyl salicylate, that weird one. And then I think wax melted second. Anyways, it melted pretty quick. Guess what wax is made of? I told you in lab. What elements are in wax? Carbon, hydrogen, and oxygen. It's organic. Wax is organic. So candle wax is organic. That means it's covalent. That also means nonpolar. Wax, candle wax doesn't mix with water. Why? It won't dissolve in water.
Polar.
Because it's polar and nonpolar. They don't mix, right? That whole video that the guys were singing. Polar versus polar, nonpolar, nonpolar, right? Get it? It was 2 polar bears and then 2 grizzly bears, or whatever they were. Not grizzly bears. Brown bears. Yeah, grizzlies are way bigger. Anyways, the point is nonpolar. So, back to my original question. Do you think these things have strong forces holding them together, or weak? Think of the wax. I need someone besides Zach to really be on board here. Well, besides a couple people. I need everyone on board. If the wax melted very quickly, does that mean it has strong forces or weak forces? Weak. I need everyone to understand that. Things that don't melt easily, like metal, this desk, the top of this, will not melt. It's very strong. It has strong forces. Something that melts easily, like wax, that has very weak forces. We've already talked about this many, many, many times. I'm just reiterating it. Make sure you understand. So, the point is, I'm trying to get you to understand here, wax is an example of an organic molecule. They have weak forces of attraction. Weak forces of attraction. Almost every organic molecule I can think of right now, for the most part, and there's like thousands of them, almost all of them have weak forces. What does that mean? They have low melting points low melting points and low boiling points. Low melting points, low boiling points. What else does this mean? It does, or they do not, dissolve in H2O very well. And there are exceptions. Okay, I'm not going to sit here and tell you this is how it is every single compound in the world. But in general, these are the general trends. They have weak forces, low melting point, low boiling point, do not dissolve in water. I'm just trying to give you an overview today of kind of what we're going to be talking about. So anything containing carbon, and then because they don't have metals in them, they're covalent, mostly nonpolar, and here's some examples of what that means. And then one other thing, if there's no metals, and if it doesn't dissolve in water, if it's covalent, will it conduct electricity?
No.
No, it has no ions. Do not conduct electricity. I'm going to put a word in parentheses. Hopefully it'll make sense to you. It's a non-electrolyte. A non-electrolyte. Electrolytes conduct electricity, so therefore this is called a non-electrolyte. They do not conduct electricity. Okay? So this is kind of just a summary of the properties of organic compounds, organic molecules. It's a lot of stuff you already know. You already knew all of this. When we write a covalent, I expect all of you to know that already. And I don't think that's expecting too much. Okay? So nonpolar, very weak, and then all the other stuff. Alright? So now that leads me to the next part of today. Oh, sorry, did I go too quick there? Are we good? Saying you good?
Yep.
Okay. Alright, next thing I want to talk about is some examples. So the first example of organic compounds or organic molecules is table Q. They're called hydrocarbons. Hydrocarbons. See, most organic compounds really just have C and H in it. A lot of them have CH and O, like sugar. But hydrocarbons are organic molecules that contain only C's and H's. Only carbons and hydrogens. Only carbons and hydrogens. And there's three types of hydrocarbons. The first is called an alkane, the alkanes. Second, the alkenes. And the third are the alkynes. And those are on table Q. So what we're going to do now is we're going to explain the difference between the three. We're going to explain the difference between the three. And then we're going to learn how to use tables P and Q. And your homework is going to be drawing and naming some structures, some simple ones though. So we're going to start out with some simple structures today. Okay. Look at the reference table Q there. Look at Q. Reference table Q. What's the difference? Don't say it out loud. What's the difference between alkene, alkenes, and alkynes? Just getting your information from table Q. What is the difference between alkenes, alkenes, and alkynes? Just looking at table Q. Sydney, got anything for me?
Structure?
The structure, good. Explain. How is the structure different? You're right. 100% right. Good job.
There's like different amounts of stuff.
Different amounts of stuff. Yep.
It's shaped different.
It's shaped different. Okay, good.
Different bonds.
Different bonds. Ooh, now we're getting somewhere. Do you want me to move on or do you want to keep going? Okay, you've done a good job. Someone else add to what she said. She said something with the bonds are different. Althea, how are the bonds different?
Going like from alkanes to alkynes, it gets stronger.
Good, it gets stronger. How do you know that? It doesn't say that on table Q.
Because there's double bonds
And triple bonds. Very good, Althea. So that's the key. So you hit all the good things, and then she was more specific. Good job. Alkanes have only single bonds. And that's the weakest. Good job. That was good that you connected that. I was going to do it, but Althea did it for me. Single bonds are the weakest. And that's what alkanes are made of. Single bonds. Alkene, they have a double bond. They have a double bond. And then alkynes, they have a triple bond. So even though all three of these are organic, and all three of them are nonpolar covalent, and all three of them are weak, this one is the weakest, this one is the strongest, because of the triple bond versus the single bond. We already learned that, though, down the road. I'm not going to write that again. You already know that. Althea proved you already know it. Good job. Triple bond is the strongest. Single bond would definitely be the weakest. So that's good. So that's one valuable use of table Q. Just looking at the example they give you, the structure. All right, I should probably get mine out. I kind of have it memorized, but I think they give you, they give you ethane, ethene, and ethine. So just looking at that structural formula, you can see the difference there. Single bond between those two carbons, double bond between the two carbons, and a triple bond between the two carbons. Anyone confused what I'm talking about right now with the structure in the picture? Okay, good. What's next here? Hey,
memorize that? Like
memorize what?
alkanes being the weakest and alkynes being strongest.
Well, yeah, because you should have memorized that a while ago. Remember I had someone breaking pencils?
Me. I wasn't here that day.
Well, just imagine if you're holding a pencil, it's easy to break. But if you break it in half and take those two pieces and put them on top of each other and try and break that, that's like trying to break a double bond. And if you manage to break that, you have 4 little pieces. Take 3 of those little pieces and stack them up and try and break those. That's like trying to break. That's almost impossible. So the single bond, single pencil is easiest to break, and then the double and triple is harder
I'm
to
just
break.
saying with like the alkanes and the alkynes.
Well,
Like, I know
you don't have to memorize that this is single bond because it's right there on table Q for you. And this is a double, and so you don't have to memorize this because it's on table Q, but I do expect you to understand that the triple bond is stronger than a double and stronger than a single. Does that answer your question? You sure?
Yeah.
Okay, yeah.
Can I wash my hands?
Sure. Well, can you wait or not? We only got a little bit of time. If it's really bad, then you can go quick. Yes.
I just want to wash them.
You did. I'll leave it up to you.
I can wait.
I'll leave it up to you.
I just want to wash them.
Okay. So now what we're going to talk about is how to draw these things. Alkanes. We're going to start with alkanes. So alkanes, again, alkane, alkene, alkyne are called hydrocarbons because they only have carbon and hydrogen. They only have carbon and hydrogen. And then if you look at table Q, what does the word homologous mean? Similar or the same, right. So alkanes are all similar to each other. So alkanes are, I don't know, let's think of alkanes, alkenes, and alkynes as like, I can't think of a great example, different types of dogs, okay? So like alkanes are like golden retrievers. So all golden retrievers have something in common with all other golden retrievers. Is that fair to say?
Yes.
But an alkene are like bulldogs. So it's different than a golden retriever, but there's some similarities, and then all bulldogs are similar to each other. And I would say 2 bulldogs are more similar than a bulldog and a golden retriever. Would you agree? So an alkane is more similar to another alkane, but it has some things in common with an alkene. Why? Because they both have carbon and hydrogen. So hope you're following me a little bit there. And then alkyne would be another breed of dog. So the concept is homologous here. They all are very similar, but they have 3 different types. So we're going to start with the simple ones here, alkanes. And notice that in the table Q example, the name of the alkane is ethane. Notice that the name of the alkene is ethene, and notice the name of the alkyne is ethyne. So notice the end of the name ends with whatever the group name is. So alkanes are ending in anes, alkenes end in enes, and alkynes end in ine. Y-N-E, that's how you say ine. So what I'm going to try and walk you through now is how to use table P and Q together to draw structures and name some simple ones. And that's all we'll do today, and I'll give you a worksheet to try and practice. All right? So here we go. I'm going to give you a couple structures and a couple names, and we're going to see how we do. So write this down. CH4, C3H6, nope, C3H8, sorry, write that down. And underneath it, I'm going to, so leave a space here. And underneath, I'm going to write a couple things here. I'm going to write butane, and I'm going to write pentane. So I'm going to show you right now how to go from the formula, so CH4 and C3H8 are the formula version of an alkane, and how to write the name. And then I'm going to go from the name and show you how to write the formula. So we're going to kind of go both directions here. All right? And then, whatever time's left, I'll have you practice drawing some structures out. So it is a little bit confusing right now, I get it. Let's get some examples down. So, if I write CH4 on the board, and I say to you guys, what is the name of CH4? Here's what you do. Here's what you do. You look at it, and you say, I have one carbon. Go to table P. See where it says number of carbon atoms? It says 1, right? What's the prefix for 1? Meth. So I know one carbon has the prefix meth. Write that down. Now, you see where it says general formula on table Q? Stay with me. If I plug the number 1 in for N, for the alkanes, how many hydrogens am I going to get? If the number 1 is plugged in for N,
4.
I'm going to get 4 because H is 2N plus 2. So 2 times 1 is 2, plus 2 is 4. So I know this formula fits the alkane formula because of table Q. So I know this is an alkane. I also know it starts with meth because table P told me so. So if I know it's an alkane and I know it's meth, now I just add the end of the name and it's A-N-E. So CH4 is called methane. Let's try the next one.
Wait.
Yes?
Why do you put in A&E?
Because this formula fits in the general formula for an alkane.
Oh, I see.
It won't fit in the alkene or alkyne because the math won't work out. See, if we take a 1 and put it in for the alkene, see where it says CnH2n?
Yep.
If we put a 1 in, we would get CH2. And that's not what I gave you. I gave you CH4.
And then you take the ending of that.
You take the ending of the name, right. Yep. Yep, you'll get it. We're going to do a lot of practice problems.
Why did you put butane underneath that?
Oh, it's a separate example.
Oh, okay.
Okay, C3H8. Who can tell me what's the prefix for 3? Yeah, it's prop. It's not prop. We say prop, so that was good. Prop. Now, again, we take that 3, plug it in for the N, and what does H add up to? 8. So C3H8 matches the alkane general formula. So I know this is an alkane, so it becomes propane. Propane. Now, let's try and work backwards with these two. If I know the name is butane, and I know the name is pentane, here's what I do. I look up B-U-T. Okay, but is how we pronounce that on table P. Table P says that's 4. So I know I have C4. And now since it says A-N-E, so butane, now I know it's an alkane. So I go to the alkane general formula and plug 4 in for N, and what does H become? 10. C4H10. C4H10. I do the same thing for pentane. I'm going to stop though because the bell's going to ring. And you know what? I'm not going to give you that worksheet. Instead, I have a review worksheet I'll give you. So we'll do the organic homework